we have already studied series resonance circuit. Now we will study parallel resonance circuit. In parallel resonance circuit, we can see resistance, inductor and capacitor are in parallel, and we will find the equation and frequency for this parallel resonance circuit. Okay. So this is supply current Is in resistance current IR, inductor current IL, and capacitor current is IC. Okay. Now we all know nodal analysis, the Is current. Okay. Is current is supply current. Supply current at this point we are taking KCL. Okay. So Is equal to Is plus IL plus IC, and the inductive reactance equal to J omega L. We are all familiar with that. The inductive reactance is J omega L, and capacitive reactance X equal to 1 by J omega C. Okay. So at this point A, if we apply nodal analysis, Is equal to, all are in parallel, so voltage across resistance, inductance and capacitor are Vm sin omega t. Okay. So Vm sin omega t by R, R equal to IL equal to Vm sin omega t by J omega L, and IC equal to Vm sin omega t by 1 by J omega C. Now Is equal to, we will common Vm sin omega t 1 by R plus J omega C plus J 1 by J omega. Okay, so Is equal to Vm sin omega t by 1 by R plus, if we common J omega C minus 1 by omega L. Okay, we are finding this equation. Now in previous case we have already studied that if this inductive reactance and capacitive reactance is same, then resonance will happen for series resonance circuit. Now for this case 1 by R omega L 1 by omega L omega C, this is admittance of the circuit. The reciprocal of reactance is called admittance. Okay. So if the admittance of the circuit is same, inductive admittance equal to capacitive admittance will be same, then what will happen in the circuit we will see. So if omega L at some frequency, omega L equal to 1 by omega C, then what will happen? Omega square equal to 1 by LC and omega equal to 1 by root over LC. Okay. Now at this condition this term will 0. So Is source current equal to, what will happen? Vm sin omega t and by R. Okay. So this is the parallel resonance circuit condition. Okay. What is the condition? If the admittance of the capacitive reactance equal to admittance of the inductive reactance, then the parallel resonance will happen. So that case Is source current is Vm sin omega t by R. So one thing you have to remember, in parallel resonance circuit Is equal to only IR. So at resonance condition we are getting less current, because in another case where in another frequency, any frequency, we will getting Is equal to IR plus IL plus IC. So at any frequency we are getting more current, because source current equal to summation of the three current. But at resonance frequency the current will be less, we are getting only IR current. Okay, and this IR current is always fixed because it is if voltage is fixed, then IR current will be fixed, resistance is fixed, IR current will be fixed. If we are not changing the magnitude of the voltage, but we are changing the frequency of the source, then we are getting at resonance frequency, we are getting less current. Okay, so if I draw the current diagram, okay, then at resonance condition, this is the resonance condition, admittance equal to 1 by R, we are getting less amount of current. Okay, so this is called resonance frequency. So what is the scenario? If we draw the phasor diagram, we all have studied phasor diagram, Vm sin omega t. Okay, this is 0 degree. So Vm sin omega t and resistance current IR, we all have studied the resistance has a unity power factor. So resistance current will be always in phase with, this is source voltage, phase with resistance voltage. Now the inductor current, we all know the lag the voltage. So in the voltage across inductor, capacitor and resistance are same source voltage because all are in parallel. So inductor current will lag by 90 degree. So this is inductor current. And capacitor current, we all know, lead the voltage by 90 degree. So this is capacitor current. So at resonance condition, what is happening? The inductor current equal to the capacitor current. So both are cancelling each other. Then we are getting only resistive current. This is the resonance condition. If we are at some frequency, that inductor current is more. Okay, so this resonance current is 3 ampere, inductor current is 5 ampere. So we will a negative current of 5 minus 3, 2 ampere. So 2 ampere is here, IR will always fix. So we will be getting a lagging current. If capacitor current is more at some frequency, 5 ampere, inductor current 3 ampere, then we will be getting a capacitor, resultant capacitor current here 2 ampere, here IR. So we will be getting a leading current. So at frequency, any frequency other than resonance frequency, we will be getting lagging current or leading current. And we have to also remember, at resonance frequency we will be getting less amount of current. Okay, so this is the at resonance condition, the impedance of the circuit is more. Now we have already derived the equation for quality factor. This is a term we have derived for series resonance circuit. So here also we will derive the quality factor. So I have already told that quality factor is a reactive power by total amount of active power. Okay, so the reactive power in the circuit in one cycle, or we can derive it IL by IR. At resonance condition, IR equal to I0. We can write source current, IR equal to source current. We also derive by ratio of inductor current or capacitor current by source current. Okay, so we are quality factor, we are deriving quality factor equal to inductor current by source current at resonance. So as resonance condition, source current equal to IR and inductor current IL. So inductor current IL equal to, we know, V by omega L, mod value, we are taking mod value, by V by R. Source current equal to, at resonance condition, source current equal to resistance current. So quality factor equal to R by omega L. This is resonance frequency, R by omega 0. Okay, this is the quality factor of the circuit. So this is parallel resonance circuit. And also we can derive that capacitor and inductor are reactive power element. The capacitor always supply reactive power, inductor will absorb reactive power. So if we want to know the resonance physically, so what the voltage across inductor and capacitor and resistance are same. So at resonance condition, inductor and capacitor are not taking any power. So what is happening? At resonance condition, the capacitor will supply the inductor reactive power. Reactive power absorbed by the inductor, and the next cycle inductor will charge this capacitor and capacitor will supply the reactive power to the inductor. So the energy of there is no loss is happening at this resonance condition. So energy of the inductor equal to energy of the capacitor. So we all know inductor energy equal to half Li square, and capacitor energy we all know half C V square. So here we can write V by IL square equal to L by C. Okay, so V by I, voltage by current is always a resistance. So V by I we can write as a resistance. So V by I equal to root over L by C. You will study in power system this L by C term. This is called characteristic impedance. In transmission line also this phenomena will happen. The reactive power of the transmission line is supplied by the capacitor. This is called characteristic impedance. At characteristic impedance, the transmission line power factor is unity, and this is purely resistive. We are using inductor and capacitor, but we are getting a purely resistive load, because at this condition reactive power not supplied by the source, because inductor how much amount of reactive power capacitor generate, that will absorb by inductor in a one cycle. Okay.